everyone. Patrick. Going to discuss a little bit about ClickHouse at DoorDash. I'll talk a little bit about me and my team, some of our use cases, specifically some TCP connection and DNS query data sort of monitoring, and also how we do some like service map dependency monitoring as well, and some lessons learned, and then where we're going next with ClickHouse. So a little bit about me, Patrick, my GitHub and LinkedIn. I'm a staff engineer here at DoorDash on our observability team, as mentioned. And before DoorDash, I worked on GIFs. If you want to know what that means, feel free to talk to me afterwards. I haven't always been in the observability space. At DoorDash, hopefully you've used us in the past few years. But if you're ever in Europe, you can also check out our sister company, Volt. And so a little bit about my team. We're part of our core infrastructure organization. So our sister teams are like our traffic team at DoorDash, who do use Cloudflare. We have compute, build and release, and some other teams, and then we have observability, helping provide insights, into the software systems at DoorDash, and basically that boils down to sort of developing and managing our metrics, logs, and tracing infrastructure at DoorDash. I want to jump straight into some of our use cases. The first is TCP connection and DNS monitoring. This really revolves around sort of eBPF, if you ever heard of that. We have a little blog post. You can search like BPF agent DoorDash, and you'll go to this blog post that I wrote about the actual like infrastructure of how we do the monitoring. But basically, we're monitoring the TCP connections and DNS traffic across all our like Kubernetes clusters and fleet. We use eBPF probes to sort of hook into the Linux kernel here, sort of attached to system calls like TCP connect, TCP close, and like consume UDP, which we use to sort of understand when TCP connections are started and closed. We use the consume UDP to actually grab out the DNS response packets that our pods are getting from core DNS, and we then process them in our BPF agent to record that data. And so we initially attempted to sort of extract insights from this, from Prometheus. That quickly hit sort of high cardinality issues that people are probably very aware with. And then we tried doing Elasticsearch as well, and it worked. Kibana was nice enough, but it costs a lot of money. And while this data has been useful many times over and over, the ROI of this huge Elasticsearch cluster just wasn't there. And so we went seeking for something better. And I don't have to sell you all on how great ClickHouse is. But we stumbled into ClickHouse after reading lots of blogs, Cloudflare's blogs, and sort of Uber, I think, had some as well, and all around the industry. And so as a high level, we sort of migrated our sort of BPF agent there on the far left side. Instead of now submitting their events directly to Elasticsearch, they now would publish them to Kafka. And we would then consume those from Kafka and shove them into a ClickHouse instance. And then we would have Grafana on the other side, which we're already very familiar with our Prometheus of using. So it was sort of natural to sort of, when you find out there's a sort of native Grafana ClickHouse data source, you're really excited to have just plug and play with that. And so, and this architecture sort of allowed us, if ClickHouse didn't work out, right, we could switch that technology in the middle and sort of go somewhere else. Very fortunate that it did. And so we started working on sort of a project we call internally Chronicle. It's sort of like our internal code name and repo for all things ClickHouse related at DoorDash. The two big things that I'd love to mention that we've really worked on a lot is sort of an internal, our pipeline for moving Kafka into ClickHouse. We call that Scribe. So it's sort of like a Kafka ingestion pipeline. It's built on top of CHGO from the ClickHouse team, and also on Franz Go, which is sort of Kafka, a native Go Kafka client. If you're ever looking for a new Kafka client to check out, definitely. I'm not like involved with them. I just say like it's a nice ergonomic sort of client for Go and Kafka. And basically the scribe, it handles all the sort of like batching and bringing those Kafka records together, because if you're familiar with ClickHouse, you want to do sort of large inserts all at once. Though I guess you can do async inserts, but we've preferred just doing large inserts all at once. And so we've sort of abstracted that away from developers. They don't have to worry about that. We have like some configuration, or like how many bytes of Kafka records are we going to consume before we then pass it on to this like a mapper interface that developers will actually implement, that takes the like slice of records and then turns it into a chproto input, which is like the chgo sort of data structure so we can insert into the ClickHouse. And I'll show some examples of like what that looks like. But another thing we also built is sort of like DoorDash uses protobufs like heavily internally. And it turns out like, you can take protobufs and look at like proto-reflect and sort of analyze them and sort of automatically generate a schema and a mapper for developers like pretty quickly. And so we make some like sensible choices, like if we see a like a protobuf enum, we turn that into like a low cardinality string, and in Go we do like enum equal dot string, and that's like the append into the mapper. And so it like removes even some of the tedium of sort of developing the mappers if you can start with just a protobuf. And so this is just some schema that we have for like our TCP data. You have typical things like when you're sort of getting started with ClickHouse, you fall in love with stuff like double delta codecs for timestamps. You learn that there's like native support for like IPv6 columns, which is great for like our TCP data, because we have lots of these addresses. Obviously, low cardinality string like pops out immediately. There's only so many namespaces. There's only so many apps and container names. So those like fit naturally sort of into our schema here. And then, when I mentioned like our scribe, like this is kind of what like, if you're developing in CHGO, what it eventually kind of, it ended up for us looking like. Our mapper has a bunch of those columns. We have this chproto input at the top. That's actually, we'll just keep, we learned to just sort of reuse that over and over instead of always like sort of allocating it every call to map. So there's actually a nice function on the chproto input where you just like reset and it just clears the columns, and then you can just go back appending. One like lesson we learned pretty quickly is that when you're doing this like mapping function, you'll sometimes come across like records that you're like, oh, I don't really want to insert it, like maybe there's an error or something like that, and you might like quit, say continue and move on to the next sort of loop. That's bad, because you're sort of going from the protobufs, you kind of see those as rows, and we're basically turning them into columns. And the moment you sort of append a few columns, but then decide, oh no, I didn't want to do that, and you say continue, you've suddenly sort of, you have a column that has maybe 100 entries and some that have 99, and ClickHouse rightfully complains to you, and you go debug it, you immediately find out. And so we sort of now have a pattern where we do a lot of the error checking and sort of validation at the very top, instead of engineers sometimes like sprinkling it through the mapper. And our mapper gen sort of handles that as well. It sort of like separates out like, oh, here's a validate function that feel free to like fill in. Otherwise, we're just going to return true that it's going to be an okay sort of record to insert. And so this is sort of like, all that's great. That's stuff like observability team sort of works on and builds. This is actually what our developers actually see when they go to our Grafana. This is like one of our dashboards. not shown here, but at the top, there's like variables of like you select your namespace, you select your container, and then the team immediately gets like a list of all their different connections or downstream dependencies that they're talking to. And this was like a 1 hour window for, I forget, like feed service or something at DoorDash. And so they can really see exactly who they're communicating with. A lot of this it comes down to our storage team uses this a lot, like when they're trying to deprecate or remove like Redis clusters or other things, they use this data to like verify that when teams say they removed that dependency, that they actually did. And not just, obviously we can check like AWS metrics and other things, but this is like that one final check that like even there's no TCP connections going to something, and so that's great to see. And so yeah, like we've had a lot of teams sort of use this data over the past couple of years, which has been great. And then yeah, just I did want to show, like, this is one of those tables that, if you've used ClickHouse for the first time, that you're like, oh wow, like, you see like the compression and everything and everything, and it's just nice to see when you're coming from like Elasticsearch, suddenly those like a few terabytes of data or petabytes of data suddenly become very small and manageable. And yeah, there's a query down here. I think I probably borrowed from Altinity or something like that. But yeah, I'm sure everyone has this sort of query and dashboard sort of lined up when they're working with ClickHouse. So yeah, that's one of our major sort of use cases. The next one I wanted to talk about is sort of like a service map. And like our service topology at DoorDash. And basically what it means is like, the eBPF data is great. But it resolves at the service and container level. And, maybe for things like databases, that's like what we're worried about. But the individual engineering teams, like our product teams, when they're developing, like they're concerned at like the endpoint level, right? And the TCP connection data can't like go and say that TCP connection was for that endpoint or that request or things like that. And so how can we help teams know their dependencies at that endpoint level? And so the obvious answer is OpenTelemetry. And so fully adopted at DoorDash, thanks to like the Java auto instrumentation. And if you decide to store span data in ClickHouse, it'll probably look like this. You might go and see like the ClickHouse exporter in OpenTelemetry collector, and you'll probably copy it. Maybe you'll make a little bit of changes, but it'll probably end up looking like this, where you have timestamp, trace ID, and everything like that. And this is great. And you'll be able to visualize traces, and you can like search for given spans and all sorts of stuff like that. But if you actually want to like analyze connections between services and endpoints at like scale, like not just an individual trace, but like millions of traces and like millions of requests, like that's a tough ask to do. You could sit there and let ClickHouse chug through it with some like expensive recursive queries and whatnot, but we attempted to do something a little bit different. The reason I'm saying this is because like if you imagine like in a trace, right, like there's all these different spans and like they're laid out like this, right? Like so there's this blue service, has some endpoint, it has some internal spans maybe. It has a few clients that's going to call, so those are going to emit client spans. And then we'll finally get these dependencies like the yellow service and the green service. And how would you write a query? Maybe someone here can figure it out to sort of like find like, okay, there's nothing in this like server span for the green service that says it was connected to that root server span from the blue service, right? Like there's some like paths of parent span ID that you can follow, but as you can see, like the yellow one, you'd have to like go multiple, and you wouldn't know where to stop, and it'd be a little confusing. And so what we really want, instead of just like every span as an individual row, which again we do that, is something we call the service map, and where we want to actually store like the edges of the graph, where we have like sources and targets. So we have like the client and the dependency, and even with this, like we still can keep some of the information, like the trace and span ID. We record if like the source thought that connection was an error, how long it thought it took versus how long the target thought it took, and so we collect all that data and store it in ClickHouse. And so how do we do that? So we heavily customize the OpenTelemetry collector, and we love writing our own custom processors for OpenTelemetry at DoorDash. So yeah, like now we ingest our span data from Kafka. The data as we publish, as services publish their span data, they go to a collector that's sort of local to their cluster. That collector then publishes the data to Kafka. It shards or it partitions the data based off a trace ID. That way, all spans with the same trace ID will end up on the same partition in Kafka. And so that way, our sort of consumer on the other side of Kafka will consume one given partition from Kafka, and it'll know that for a given trace ID, it will always have, it should get all the spans for that trace ID, which then allows us to use the community-provided sort of group by trace processor, which actually sort of takes in the spans, has a little like wait time, and sort of builds up a trace with all the spans of the same trace ID, and then publishes the next step. And then we wrote a custom service map processor to actually do the work of sort of walking that trace, sort of like down the dependencies, skipping over the correct internal spans, doing the connections, handling sort of interesting dependencies around like cadence and some other things that don't like typically follow sort of server client sort of setup. And then that processor sort of as a side effect does what the sort of BPF agent and our eBPF flow did. It publishes to Kafka. We consume we consume through our scribe and then write it happily into ClickHouse at the end. And so what does that look like? Of course, it turns into another Grafana dashboard because I'm on the observability team, so that's what I do. So teams can come visit here, and they can, at the top, again, I'm hiding the variables. Sorry about that. They select, I think this is like our ad service. They select what endpoint, and then they get a list of, a graph that's just there to look pretty, though it doesn't look that pretty, but it doesn't offer that too much. But, it gives them a list of all their clients. Ideally, they should know that, but maybe they don't. And then it gives them a list of all their dependencies. The clients and like most of the dependencies table and the service graph are actually computed off of materialized views. So when the data flows in through our service map, we actually have a materialized view that sort of rolls it up into 1 hour windows, because for the most part, people don't really need every single connection. They just need the aggregate. So all that is sort of done with the materialized views. But the thing I do want to point out is sort of like this appears and fan out column. That really comes from the power that, yes, I do get to keep all the raw data, and I have like the span ID and the trace ID. And so I can do some like SQL queries of like counting the uniques, getting the estimate of the unique really quickly in ClickHouse, and sort of knowing like, for every dependency, like how often does it appear in this endpoint's like dependency graph, right? Like for the most part, it's 100%, but there are some calls at the bottom that are like 20 or 10%, which probably signals that they have some, sort of maybe they're doing some testing, experimentation, or they have some like if branches that like rarely get hit. And so they can sort of see maybe the complexity of their endpoint beyond just sort of looking at the code, right? And then the other one is called fan out, which is basically saying, okay, when this dependency appears, how often are you actually calling this, right? Like, there's some that's clearly just one call, right? But there are some that are sort of like, okay, when it appears, they're actually making this call twice. And maybe that's a reasonable thing that they need to do. but it's also been helpful for teams, and we've had teams like discover that they're making a dozen calls to some dependency, and they realize, oh, we should probably fix that. And so like this has been super helpful, and it's all been sort of powered by the fact that we have sort of billions of these edges in there, and we can give really accurate estimates of this sort of fan out to people. Yeah, and that's two of our main sort of use cases we've done so far. Just wanted to share some lessons that we've learned. It's not many, but there's many more. I'm sure lots of people have shared similar things. One, we found sort of recently, we now avoid distributed table inserts. Previously, we would just sort of like insert directly or insert into our distributed table. But we're already writing our own ingesters, so like why are we don't really need to rely on ClickHouse to do the sort of load balancing of the data across the sort of underlying merge trees. And so we turned to relying purely on client-side load balancing. And so this graph here at the top is sort of like, that's what happened when we went from, I think this is my graph of the merges happening on our OTel cluster, that we went from sort of just putting into our distributed table to just hitting directly the local table. It like dramatically improved sort of the performance of the cluster, to be honest. And also, it also reduces a lot of the money we have to spend AWS, because now no longer does the data, we're obviously paying cross-AZ traffic, and then ClickHouse is gonna double that for fun. So we stopped that as well. Another one, this probably should be obvious. It wasn't to us at the time. Monitor your disk throughput, especially if you're using EBS volumes. Our OpenTelemetry cluster would actually come to a halt at some times. Turns out during S3 uploads, ClickHouse was more than happy to use all the bandwidth to send that data off to S3, which actually it was more than happy then to read all that off of our EBS volume at that time. And so if all we're doing is reading, we can't write, and so the cluster comes to sort of a halt. And so we moved to sort of, we attached much faster volumes to the cluster, and now when data flows into ClickHouse, we put it on the fast volume first, and then we have sort of some storage policies that can move it to the slower disk or then off to S3. And then lastly, if you do use CHGO and you happen to use nested columns, they can just be modeled as sort of array columns. You don't have to like wonder about call nested or something like that. So like with the OTel stuff, it's sort of like a column of arrays and so on. And so even for like a nested that has like a map type, you can do like a column of array and the sort of map. It's not immediately obvious from any documentation that I could find, but eventually we sort of figured it out and made it work, which was great because we really did want the OTel like event data that appeared on spans, because that normally includes things like exceptions and whatnot. And so it was great to finally figure out like how to get that into ClickHouse, so then we could build sort of like exception browsers and some other stuff in Grafana, which was nice. And so, yeah, what's sort of next for us at DoorDash with ClickHouse and whatnot? To be honest, we're patiently awaiting the non-experimental JSON. We really want to adopt like tracing as sort of like the first-class citizen for observability. Maybe you've read some blog posts over the past year about this concept of white events and whatnot. But we really want to move teams to sort of context-rich sort of events per like hop in our distributed ecosystem at DoorDash, and sort of model those as like OpenTelemetry spans. And sort of this mantra is like that log line you had really should have been an attribute on some like span data. And then pushing for like semantic conventions that are sort of shared across the organization. So the same ID is used everywhere, the same name, the same attributes is all used the same everywhere. And obviously then we definitely want to store that data in ClickHouse. And that like new JSON type is very exciting, sort of aligning with semantic conventions, because now we'd be less afraid of like a dynamic explosion of sort of like attributes that we're storing. Like it could be limited. We could give it the type hints that the column can take and things like that. So yeah, that's sort of like where we're going next. And then one last thing, I wrote these slides, like a week ago, and then over the weekend, I was doing, maybe other people do it, Advent of Code, which is sort of like a daily programming puzzle sort of throughout the month of December. Typically, people do them in like Python, or you're weird and you do them in OCaml, like I've done for the past few years. Or maybe this year you're doing it in C++ because you want to learn to maybe read the ClickHouse source code. But could we actually do these problems in ClickHouse itself? Because like ClickHouse SQL is quite featureful and expressive, and ClickHouse Local exists, and that can be sort of our runtime. Sorry for diverging completely from the talk that was previously. So here's some spoilers for day 2. So if you actually do this, I'm sorry. But here's like the solution for day 2 in ClickHouse SQL. So we can parse the data, right? Like down here at the bottom, I can read the data in. I'll do line as string. Didn't really care for that. Kind of wanted to figure out how to make like the TSV or CSV just kind of work with the input, or I know there's like a special one where you can pass in the format, but I couldn't actually get it to work. Maybe someone else can figure it out. That'd be great. So I just pass it in as line of string, and I'm going to use stuff like split by char on like the spaces to get the integers. So like in day 2, every line is sort of like a sequence of integers, and so we want to parse that, and so we're going to use split by char and then array map to turn those into ints. And then part 1 is asking us sort of like how many sequences are sort of monotonically increasing or decreasing and are bounded like difference between the elements. So like it's either always increasing but never increasing by more than 3, or always decreasing and never decreasing by more than 3. And so you actually can do that, like, right? You can use the array difference to get the deltas between all the elements, and then you have to run array pop front because the first element is 0, which you actually kind of want to ignore, and then and then we pass in the logic that we're going to do with like array exists, make sure that everything's sort of below absolute value of 3. We'll then sort of make sure that they're all increasing or decreasing with array all. And that gives us like the valid. And then at the bottom, we can just do count if valid, and that's part 1. And then part 2, if you've done Advent of Code, they always throw in a little wrinkle, which is like, okay, if you're allowed to delete one element from the sequence, how many then can be made valid? And so how do we do that in ClickHouse SQL? My idea was, okay, we'll use array enumerate to sort of get the indexes, and then we'll use array map, and we'll sort of go over the indexes, removing out one element from each using array filter. And so now you have an array of arrays. And so then you do like array map on that, right? And then you're sort of repeating it over and over until you get down to the bottom where we get this sort of fixable thing. And so part 2 is just a simple sort of count if, valid, or fixable. And there, yeah, you get day 2 just right in ClickHouse, which I thought was a pretty fun sort of thing, as someone who does sort of Advent of Code every year. So yeah, that about covers it. Thank you so much for listening. It was great being up here. Thank you. I didn't know if there was any questions.
Great, thank you, Patrick. We can take a question or two, and then we got to get to the next speaker.
Yeah.
I'm over here, yeah.
I have just a few improvements for the previous query. Could you please open the previous slide? Just a few tricks. First of all, you can make this SQL script executable. Just write hashbang.
Oh, right. Okay, yeah.
And it will run as a file, as a script. The second trick, you don't have to specify the structure. If you specify line as string, the default structure will be one column named line with type string. So you just write line here. And most likely, you even don't have to specify the line as string format. It should be.
I think the only reason I had to do this is that I got back a nullable string, and this somewhere in here did not like me passing in nullable. So I think line of string forced me to tell it that I definitely have a string on every line.
Okay, and it was not a question, so a real question. How did you know about ClickHouse in the first place?
Oh, that's a great question. As a user of Cloudflare, we'd seen it through passing of reading their blogs. We had some engineers who came to DoorDash from Uber, which had previous experience with ClickHouse. So yeah, I think it was more of an osmosis of like other engineers who came to DoorDash with that experience, mentioned it in passing, and then the observability team, as mentioned, like we were sort of looking for an alternative to Elasticsearch for us. And so, yeah, it was sort of like something we sort of learned from other engineers at the team at DoorDash.
Hey, loved the talk. Loved the. I would not have thought to do that with Advent. So this is a really specific technical question, and I'm curious if this was just old code or if there was a decision here. So this is in mapper gen when you were going through the interface in Go.
Yeah.
The very first field was mapper H,
yes.
and that was still a Prometheus histogram.
Oh.
So I was curious. I was curious if that was intentional.
Yeah. So truthfully, the mapper I did share was pre-mapper gen. So like we wrote some by hand and then decided, oh, I can repeat that. Yeah, we do actually pass in still a Prometheus histogram because we are like, we heavily use Prometheus for monitoring at DoorDash, and so we use that as sort of like an outside of, a secondary like monitoring, like how like a lot of the records that we're consuming have like a timestamp on them. And so we look at those and be like, oh, how old is this? So we can be like, oh, is our scribe like up to speed? And so, yeah, it's sort of like a, yeah.
Yeah, makes total sense, yeah. I was just curious. All right, great, yeah, thank you.